Hello guys, welcome to my channel, and in this video I'll explain you article number 2.7, potential energy of a system of charges. So let's start. Consider first the simple case of two charges q1 and q2 with position vector r1 and r2 related to some origin. Okay, so we are given two charges q1 and q2 and their position vectors are r1 and r2 with respect to some origin. Okay, let us calculate the work done externally in building up this configuration. So how much work we have done to bring this charges closer, or we can say the to build this configuration of charge, these two charges. So we'll calculate that work done. This means that we consider the charges q1 and q2 initially at infinity and determine the work done by an external agency to bring charges to the given location. Okay, the first of all we consider these two charges were initially at infinity. Okay, and we will bring them from infinity to their respective points one by one. Suppose first the charge q1 is brought from infinity to a point r1. There is no external field against which work need to be done, so work done in bringing q1 from infinity to r1 is 0. Okay, so first of all what we'll do, we'll bring q1 from infinity to this point, the r1 position. Okay, so what is the work done here? So I'll say there is no work done, because what is the potential at this point? There is no potential because there is no electric field here, so there is no potential and the work done is 0. Okay, for bringing the charge q1 the work done is 0. But what is the work done in bringing the charge to q2 at its point, that is the position r2? Now there is work done because due to q1, because already we have already bring q1, so it will have some potential, it will have electric field around it and it will have some potential. This point will have some potential v1 due to this charge. And what is the work done? We know work done is charge potential multiplied by the magnitude of the charge. So the work done in bringing q2 will be from infinity will be potential v1, which is due to the charge 1 times the magnitude of the charge q2. Okay, so the charges produces a potential. Okay, so the first charge will produce a potential at any point, any general point, that v1 is equal to 1 upon 4 pi epsilon naught q1 r1p. So this is the potential due to point charge that is studied in the previous lectures. Okay, now we are r1p is the distance of a point p in space from the location q1. Okay, from the definition of potential, work done in bringing charge to q2 from infinity to the point r2 is q2 times the potential at r2 due to q1. Okay, I have already explained you this just now. I have explained you the work done will be v1 q2, potential at that point due to q1 multiply the magnitude of the charge q2. Okay, potential of due to q1 was 1 upon 4 pi epsilon naught q1. There will be r12. Now the distance is r1p was for any general point, and this distance will be now r12 for this point, r2 point. Okay, so now and multiply q2. So this is the work done in bringing q1 and q2. This is the work done in bringing q2. So total work done will be same. Okay, now since where q r12 is the distance between points 1 and 2, since electrostatic force is conservative, this works get stored in the form of potential energy of the system. Okay, so we know that electrostatic force is conservative. I already explained it to you. Okay, so this work done will be stored as potential energy. Thus the potential energy of a system of two already charges q1 and q2 is this much. Okay, so this is the work we did in bringing two charges together, and this will be stored as electrostatic potential energy of the system. Okay, obviously if q2 was brought first to its present location and q1 brought later, the potential energy u would be same. Okay, it doesn't matter which charge is brought first. You will see that in both cases, whether either I bring the first charge first and the second charge later, the potential energy will be same. More generally, the potential energy expression is unaltered whatever way the charges are brought to the specified location, because of the part depends on the work for electrostatic force. Okay, because in the conservative field, so what will happen, it doesn't matter which path you bring the charges, the potential will be same. It only depends on the points, and also which charge you brought, this doesn't matter. Equation 2.22 is true for any sign q1 and q2. if q1 q2 is greater than 0, potential energy is positive. Okay, and this is true for any charge. Okay, any value, any sign of charge, even if it was both yeah, if q1 and q2 are greater than 0, that is both charges are either positive or both are either negative, potential will be positive, potential energy will be positive. And if this is expected, okay, so what does positive potential energy means? That there will be repulsion between two charges. Okay, positive potential energy, it's want to be, it is unstable. Okay, and now this is expected since for like charges electricity force is repulsion and a positive amount of energy is needed to do it done against this force to bring the charges from infinity to a finite distance apart. Okay, so what we did, we there was a force of repulsion between these two charges, and we did work against the electric field repulsive force, and we brought them together, so they are now stable, they will exert repulsive force. So you have to remember, u negative, u positive will be repulsive, the system will be, the charges will repel each other. And what if the two charges are of opposite nature, that is one minus one positive, then u will be negative and there will be attraction. It is the more, the less the value of u, the more stable is the system. Okay, now for unlike charges q1 q2 less than 0, the electrostatic force is attractive. In that case, a positive amount of work is needed against this force to take the charges from the given location to infinity. Okay, in that case what will happen, if I have to take the two charges to infinity, I have to do work in a, now in order to separate these two charges, I have to do work in this case. Okay, so potential energy will be negative in this case. Okay, in other words, a negative amount of work is needed for the reverse part. Okay, so in order to take these charges apart, I have to do work. Okay, this opposite charges, in order to bring the charges, I have to negative of this work. Okay, that's why the potential energy is negative. Okay, and now equation 2.22 is easily generalized for a system of any number of point charges. Let us calculate the potential energy of a system of three charges q1 q2 q3 relative located at r1 and r2 respectively. We did this it for two charges, now we can do it for three charges also. So what is the procedure? This is same procedure. We bring the first charge first. Okay, there will be no work done in that. Then we bring the second charge and there will be work done against the potential of the first charge. Okay, then we'll bring what, we'll bring the third charge, and when you bring in third charge, what will happen, there will be work done against the potential due to first charge and the potential due to second charge. So we'll add the three work done and we'll get the total work done, and that will the potential energy of the system. Okay, so now to bring q1 first from infinity to r1, no work is required. Next we bring q2 from infinity to r2 as before. Work done in this step is this much. This is similar to the first case. Okay, now the charges q1 and q2 produce a potential which is at any point is given by this. Okay, now we have brought q1 and q2 and any general point, what will happen, they will exert, they will have potential because of these 2 points. That potential will be 1 upon 4 pi epsilon naught q1 upon rp1. This will be rp1 distance, this will be r2p distance. Okay, and now work done in bringing q3 from infinity to point r3 is q times this. So similarly, so what will the work done, the work done will be just multiply this by the q3 and we'll get the work done bringing q3 at the that point. Okay, so the work done in bringing r3 at this r3 position will be, third charge at r3 position is 1 upon 4 pi epsilon naught q1 times q2 1 r3 plus q2 upon q2 into q3 upon r23. Okay, I hope you got this. Now the total work done in assembling the charge at the given location obtained by adding the work done this step. Okay, so this was the work done bringing third charge, this was the work done bringing second charge, first charge was work done was 0, so adding the 3 will get the potential energy will be 1 upon 4 pi epsilon naught q1 q2 r12 plus r q1 q2 upon r13 plus q2 q3 upon r23. We can find, similarly we can find the potential for n number of charges. Again, because of the conserving nature of the electrostatic force, the final expression for u is independent of the manner in which the configuration is assembled. Okay, so it doesn't matter which charge is brought first, and because it is part independent. The potential energy is characteristics of the present state of configuration and not the way the state is achieved. Okay, so so the position of these two charges is will decide the potential energy system, and not the way we have, the path we have followed or the way we have achieved. It doesn't matter, only the present position matter. Okay, so I hope this paragraph is clear to you now. Okay, in the last next paragraph we will discuss about potential in the electric field. So it will be very similar to this, but there will be additional work done because of the external electric field. Okay, so that will discuss in the next paragraph. Thanks for watching. Do like, subscribe and share this channel.